Okay, so let's get started. We are week number 10 of the semester, so I hope you guys are already having some good experience with the next project, project 2. So there will actually be some, I guess it's unavoidable that some of the groups are maybe not the same as you had in project 1. Let's get started. Okay, just saying, so if you're searching for team members for the new project, and also if you want to think a bit which projects do you want to do, maybe your teammate wants to do another one, then that's okay. It's okay if there is a change. I guess there are many teams which have now like one member changing, which might be an issue. So many teams are searching for a member. Just use this forum on Moodle, and maybe if you're a team of 2, some will also have to consider joining another team. Yeah. So, but hope that's going fine. You still have time, and take a look. Don't forget about the second project. It's a bit more interesting than the first one. It's more of a real machine learning problem. It's not like a toy data, but really real challenges where you can actually do some nice contributions by adding a bit of novelty. Can you hear me in the back? It's good, or louder? Okay, so that's one thing I wanted to say. The other thing, don't forget to fill out the course evaluation online. We need to get some feedback. It's valuable for the next iterations, of course. And yeah, that's it. We were almost done with the expectation maximization algorithm last time. This was an algorithm to optimize generative models, to optimize mixture models, Gaussian mixture models. I'll just do a very brief recap to remind ourselves where we've been last time. We wanted to maximize the likelihood, right? So this was a function which looks maybe like this. It's a very complicated function, but it has the optimum at some point, so maybe this is not the ideal figure. So maybe it's better to think that our likelihood somewhere has a maximum. So, and we want to find it. Okay, if that's my likelihood function, I'm plotting this on the y-axis, then you can imagine like here there will be a maximum, right? So, and you want to find that point. Sometimes we call this the star, right? The optimal parameters, which would make your data most likely to happen under that model. That's what we want to find. The problem is that the likelihood function, L of the parameters, is quite a complicated function, right? It's not a nice concave function where there is only one local maxima or something. It's something a bit nasty. That's why we cannot just optimize this in one step, but we want to have an iterative algorithm. So what we did is we defined these approximations to this likelihood at every point. So at the current point where we are, right, we build a little simplification of the model, and this was this purple curve when I'm currently located somewhere. So these curves, these models, they depend on two things, right? They're supposed to be functions of the parameters as well, but they're supposed to be simple, and then they depend on where you are. So that's why here this was depending on two things, right? It's a function of the parameters because we want to, that's the objects we care about. We want simple functions which we can maximize. And yeah, we need to describe them somehow. So it depends on what this model actually is. This one, right? It depends both where we are, theta t, that we fix for the moment to make our life simpler. And that's how we get this curve here, right? By talking about one particular position, and let's define a function now, a function on depending on the theta. That's the idea. That's what we want to do. Then we just maximize this simpler function instead, and that's giving us the next position. And then, so now we have moved to this position, And we do the same thing again. We build a simple model. So you can imagine this as very simple round functions. We maximize that, and again we go to the next point and next. So eventually we get closer to the optimum. That's the hope then. And yeah, actually in every step this will actually improve the likelihood. We haven't proved that, but you can actually show that. Then yeah, this was a little bit technical, but it's still a very good instruction for you to first of all understand a bit these probability notions. What does it mean to be coming from a generative model? And then I'll comment a little bit more on the proof technique we used here. So first step is how to actually define these models. And that's what I just want to do a brief recap. That was a question?
So we can see that at every step we actually, like L gets bigger, right? But after, can we actually get stuck in a local maximum?
Can this get stuck in a local maximum? So let's say it could get stuck here. Yeah, it actually could. So I'm not aware of any proof which would show that this can be avoided. So yes, this could happen. But still, in every step, we will at least a little bit improve. And this is a very hard problem, so that's the best we can do. So at least it's a method that is quite fast per iteration, but we don't have a proof that it will lead us to the best point, which is over here. Okay, just the proof technique to define these models for a fixed position of interest, the parameter t. We use the Jensen's inequality. It's actually, yeah, this is the definition of convexity or concavity. It's equivalent, right? So you can call it a lemma, or you can just call it a definition, whichever you prepare. So this is a bit the optimization perspective, right? We would prefer to have concave functions if we maximize. And whenever we do proofs in optimization, this property is basically the only thing we have. So you will always use this property. And that's what we also use here to actually transform the original problem and instead get these simpler lower bounds, these guys. So that's the definition of the lower bound, right? So let's try to again understand why this is true. We said this inequality of convexity is true whatever convex combination weights you use, as long as you use some weights which sum up to 1 and are non-negative, then you can use this definition of convexity. What does it say? It says nothing than that the combination of these function values, it will lie below the function value itself. That's the definition of concavity or of convexity of minus this function. That's what it says, so now we can be creative what weights we want to use. This was maybe a little bit confusing. Why did we put some weights here and here? The only reason is if you do that, if you put them both ways, then here they will cancel out, right? Because here you will have the weight and divided by the weight. So they cancel here, and that's the only motivation, because we want to talk about the quantity on the left. This is the likelihood. We want to get some information about it. So by defining the R values, which are the points you use for the convexity, if you choose them like this, then on the left side you will just get what you want. That's why we have, it looks a bit strange that the weights are only on the right, but that's, believe me, there is no magic. Still, this equation, or inequality, this is true. Whatever you use for the QKNs, as long as they're non-negative and sum up to 1, you do have this inequality, so you can say this is a model which you could use. Now the only question we ask is so it's a lower bound. That's what we have already achieved. Now the second thing is Now, yeah, which Q should I choose? And that's another simple arithmetic trick, so you can really see it easily if you plug it in, so that if you do choose these guys, they sum up to 1, then what happens is that the right-hand side will be equal to the left-hand side if you look at the particular point theta t. So if you choose them this way, then what you have is that nicely they will happen to coincide at this one particular position of interest. So at the point here. So that's this equality here that I'm talking about. For this particular choice, you can easily check that, yeah, this becomes an equality, so they happen to touch at this point. That's why it's a good model, right? You are locally there, so the best information you have about these parameters is what you currently have, so you're going to use those to describe your model, but you fix them to that particular time point t, and that's the whole idea. So you fix them for a moment and you only optimize the blue guys, which make life simpler to optimize. And that's what we showed here, right? So if you choose the Qs that way, then yeah, this happens to be equal. So, and we already know it's a lower bound. Okay. Then, yeah, sorry, the notations might look a bit scary, but it's really not. We have now built the model. The next step is simpler. Now we just maximize the model. So now we have one of these approximations, right, the purple function. Now we just maximize it using this simple trick to setting the gradients to 0. That will give us the next parameter. So that step is going to bring you from here where you are to the point here, which is the maximizer of your model. So that's how you go from the parameters t to parameters t plus 1. That's the maximization step, the formulas we discussed last time. So that's all there is. This is the summary. Computing the model, that's computing these Q quantities. They depend only on your fixed current position. They don't depend on varying parameters, right? So you fix these. Now, once you have fixed them, then you actually optimize the parameters. So these are the new parameters. And they're defined to be the ones which maximize your model. And that's the updates that we got when we computed gradients to 0. So this is the whole algorithm. And then you repeat, go back to do another of these E steps. This means so expectation step, and the M step to maximize the model. The last thing we discussed was also that why is it the same as k-means? Then, so why is it a generalization of k-means? And that is also not so hard to see, but it takes maybe a minute to convince yourself. So now we look at the limit process, right? We look at what happens if all these clusters become very spiky. So you can imagine normally these clusters look quite flat, right? Everybody's normal distributed. So now this is if this is your covariance matrix, then your cluster is all spread out over the space. But if you happen to have a very small covariance matrix, so then the clusters become very spiky, very concentrated. And in that case, if you make them very, very concentrated such that the clusters become a point, then you get the k-means algorithm. And why is that? So it's not super obvious, right? But you see it here. So when you look at the normal distribution. So this is asking, yeah, for one point, compared to the cluster K, right? So what you do is, if you compute this, it depends on how far you're away from the cluster center. So the normal distribution is defined using that, right? So it's this exponential which depends on this norm, right? So now when the covariances become very small, then the values in the exponential, they can become very large. So which one is going to win? So because look at this quotient here. What you're doing is you're comparing it for one particular k. So for that k, you compare it to the average over all k's, right? So what you do is you compute your distance to all the cluster centers, and each one gets you a probability. So they're just defined by the normal distribution of each mean. Now you can imagine which one is going to win, right? So if they all, like, they explode, right? They're largest when you are closest to that particular center. So the one that's going to be winning and giving the highest value in this quotient, that's the one where you're closest to the center, right? So that one will have the highest value in the exponential, the k for which you're closest. So that quantity here will be largest for that k. And then when you just divide by the average, so the largest is going to win, right? And when they become more and more concentrated, then the difference between these values become very, very high. So one exponential will basically be almost infinity if you happen to be very close to that center, and the others, you're much further away, so we'll have a much smaller value. So what happens is that this quantity here, the k, is going to converge to the maximizer, right? That k which minimizes the distance to your cluster. That one is going to win, and this winning thing is also known as the soft max, right? Sorry for my confusion between max and min, but what I'm saying is that the maximum value of these k values is going to win because they're inside exponentials. So that quotient will almost be the same as that k for which the exponential is maximal, which means that the norm, the distance, is minimal because there's a minus in here. So think about it for a second, and again, this is only in the very simplified model that if you assume the covariance to be spherical, so just that everybody's just the identity, and everybody is very concentrated, then what I described is going to happen. And then what happens is that, the Q's will go to the assignment matrix. So there will be 1 for the winning guy, the one which you are closest to, and there will be 0 for all the other k's. And that's exactly what we had in k-means. We had everybody was assigned to what? Was assigned to the closest cluster center. So that's this limit process. So, yeah.
The k means the cluster center does not have to fall onto a point, but as I understand here in this mixture model, this explosion happens when the cluster center is on a given point, and then.
Are you asking about the cluster centers being points or not? So that's not what this is about. So this is a different thing than the phenomenon we had in Gaussian mixture model at the end, that this thing was becoming degenerate, right? Was going to infinity when they collapsed to a particular data point. So it's a related phenomenon, but it's not the same, right? So here you could really make the likelihood infinity by putting the cluster center onto one particular point. So that's not what I'm talking about. So here what we're talking about is just the cluster centers. They're not points. They can be anything. So what I'm saying is true for any positions of your cluster center. All I'm saying is that this quotient here only depends on which one is closest to you. That one will have the biggest value in the quotient. So do you agree with me on that? That the one which is smallest, because it's exponential of minus the distance, the one you're close to will have the largest value in this numerator, right? And now that's the key observation you need to make. So if you have that, now you ask what happens when the sigmas go to 0, when they become very small. Then all that happens is that the one which is already closest will be even more contributing compared to the others, right? So when you let the sigmas become very, very small, then the one which is smallest is going to win in this quotient. And that's why the q's will then almost become, so they will slowly converge to this 0, 1 vector, right? 0 for the ones you're not closest and 1 for the one you're closest. But it's only in a limit process, so it's not exactly the same for a particular sigma. But yeah, the Gaussian mixture models are more general than k-means, that we already convinced ourselves. And what we have now is that also this new algorithm which we have introduced, also that algorithm is now a generalization of the k-means algorithm, right? Because it computes these more general quantities, and it could, in the extreme case, still be almost the k-means. Yes, and also the mean update, of course, is very familiar. Again, if you would say that, yes, this is the same assignment, then also this mean update would be exactly the same, but only if they really are 0, 1. And yeah, if you want to have k-means, what you do is then also you would drop the update of the covariances. So because there is no update, you have defined your covariances to be the identity for the simple case, then you don't need to update them. By the way, that's a very okay variant of the EM algorithm as well, if you want to play with Gaussian mixture models, to do the simple version first without the covariances, and then as a next step you can see if you can gain if you also update the covariances. That means if you allow them to become non-spherical. I think that you experienced a bit in the lab last week. And if you can also update your k-means code if you want to play more, you can update it to become the EM algorithm if you're interested. So let's actually discuss an example, and then we are almost done with that. Can also discuss more, but let's be very concrete. So this is a very nice unsupervised method, right? We're just giving green data points. They have no labels attached to them. And we're going to kind of soft cluster them now into two kind of distributions, or two Gaussians, which you're going to learn to fit them. So initially, let's say they are here and here, the Gaussians. And now we're going to do a step of our EM algorithm. So now we do a expectation step first. So to go from here to here. What does that mean? It means we build the models, these purple models. So what we do is we compute the Q assignments. So they're not really assignments, right? But these are the quantities which define our model, and you can think of them as soft assignments. That's the first step. Then the second step, that's the M step. Okay, sorry, just to visualize what I've done in the E step is for each point N, I've now computed two quantities, right? The Q1 and the Q2 for that N. So each point is kind of two of these color contributions. It's a little bit blue and a little bit red. And that's what's visualized here. So that point here is almost only blue, but you can see that the ones in the middle, they are mixed, right? They are half blue, half red. And that's exactly the quantity I just tried to convince you is the mix going to the hard assignment in the extreme case. So here you can again see it depends on how far you're away from the centers in the spherical case. So you can see it's a very nice coloring, very simple, just your color is determined by which one you're closest. Computing the Q's, that's what we have done. Now we have this model. Now we will find the parameters maximizing it. What that means is we're going to find new parameters, so find new centers and new covariances and new pi's. So that's our parameters. So that's the new guys. I will get new centers, new covariances, and new pi's, right? The pi's was just the weight of each group. How big is it, kind of? So what you've seen is the blue distribution. The blue Gaussian has moved a bit to the center, so has the red one. And they have adjusted their shape. That now they became a bit elliptical because that better explains the data. So remember the M step asks for the parameters which makes this simple model most likely. And here what it's saying is that these two ellipses, they make our situation most likely if our model is the simplified model, so the purple model. Okay. Now we have done one round, so we go to the second round, we again do the E step. So now the Gaussians stay the same, but every point gets new colors. Everybody gets new values for blue and red. So yeah, it doesn't look like much has changed on the image. But now I'm going to update the centers again using an M step. Now you can see that they start to separate a bit more. So the blue one goes a bit down and the red one goes a bit to the left and up. And finally, one last time, I compute the assignments, or they also called the responsibilities, these Q values. And now, so seems like a nice clustering now. So he has found the two clusters, and the points belonging to the red cluster, they're like completely red, and it's well separated in between. So it's a nice solution it has found. So almost the points are assigned with high confidence, so they're almost only red or only blue, except the very few ones in the middle are maybe a little bit purple, so that's where we use the soft assignment. It's found a good clustering. It's a little bit elliptical, but not very much. So it's, if you would run k-means on the same data set, the solution would look quite similar. Okay, so that's EM, EM, and E. Does that make sense, more or less? Okay. Then we are almost done. So what we have done so far was a bit more from the algebraic side, right? We have seen this is the likelihood. Let's think how to maximize this function. So just from an optimization perspective. What we have not done yet is like the interpretation, like why would you do that? So does this make any sense for a probabilistic model in general? And what are these Qs anyway? And that's something that is quite easy to see when you talk about the so-called posterior of your model. So what's happening here is, so what we are claiming is that I'm claiming that the Qs have a simple interpretation. I'm claiming that they are actually probabilities, and some very special probabilities. I claim that they are the probability of the hidden variable given the data. So that's called actually the posterior. So okay, just to get notation a bit clear, so you have this long formula, and so this is just a naming thing, actually. So the first quantity we have after the equality is called the likelihood. Then this thing is called the prior. This is called the posterior. And what's the last one called? Anyone remembers? So the last one is actually, we have seen that before, but Anyone remembers the last one? It's just naming, it doesn't add insight, but it has a name. It might look familiar with what we did with the Gaussian mixture model when we got rid of the sets. So the marginal likelihood, actually, it's the marginal, yeah. Yeah, maybe that's what I heard, yeah. So probability of x, that's the marginal, right? It's because it's probability of x, no matter what z is, I don't care about z. So it's marginal likelihood. Okay, yeah, so what's this line anyway? This is really, nothing has happened, don't be confused by the formulas. This is nothing than base rules which you have, what we have written here. So all I'm saying is that probability of two events, the joint, so yeah, first one is the joint. All I'm saying is that this is P of A times P of B. And I'm also saying that you can do it the other way around if you want. So it's probability of B given A, conditioned on A, times probability of A. That's all that's there, right? There's no magic, just giving names to these things, yeah. But so far so good. So what we want to do now is we want to understand the EM algorithm in this context, right? So and what's happening with these Qs? Are they really related to this in this way? So right, because the joint thing on the left, this was much too complicated to optimize. We do not observe the sets, right? They are latent variables. They are invisible to us. They are very important. They define from which cluster you come, but we don't observe them. We're not sure. So that's why they're latent variables. So some magic has happened to get rid of the sets, which reminds you of what happens with the mixture model when we did marginalization. And actually the same trick is also happening here, and that's going to explain what the Qs are. So let's see if I can get this right. So I'm claiming that, let's try it from this thing here. Let's look at the posterior, and let's try to prove that this is actually the Q variable. So we are talking about the probability that your hidden variable is happening to be k, given that data is x. Okay, that's the quantity I'm interested in, and I now want to see how it relates to my Q, if it's really the same thing. So what do I do? How would you approach this? Yeah, you're saying I should use so I'm solving for this, so I should use the likelihood times prior, that's what he's saying, just solving for that, taking it to the other side. So what I'm doing is I'm applying base rule. That's exactly what we're going to do. So that's actually a nice thing if we think a minute that, yeah, whenever you have dealing with generative models, with probabilities, then the most basic thing you can apply is base rule, which is very important, and that's why it's kind of interesting that this tool also appears here. And on the other hand, we've seen on the optimization side, the only thing we can use, or well, in most of the optimization proofs, we use convexity, right? So, and that's exactly what's happening here in the EM algorithm. So we have actually used both of these nice tools if we manage to get to this proof here. So we are not done yet. Let's see. So what you said is I'm solving for posterior. So you're saying that this is likelihood, whatever, times the prior divided by the marginal likelihood. right? Okay, that's all we do. So let's try to do this in formulas. Okay, likelihood is yeah, let me do it in 2 steps. It's P of x given z times P of z. Okay. Now, what about the marginal likelihood? So it's P of x. And so how, sorry, I should write a bit nicer. It's P of x. I'm not writing the parameters there. Everything is conditioned anyway on them. Okay, so how can we express P of x, which is this thing here, the marginal likelihood? So yeah, you're saying I can expand it. So how could I do that?
Sum over.
Yeah, you're saying it's a sum over the whatever z can be, right? So we're talking about P of x, no matter what z is. So let's write this more precisely. P of x. I can expand it over all the possible things that the z can be. So here is all the things z could be. So right, we're talking about Zn, these hidden variables. It can be all the possible j's. I have no idea which one it's going to be. So okay, but that's what it is, right? This is just P of x. So all of this, it's the sum over all possible events, P of x and z, right? You could also just sum over the joint if you want. So that's the denominator. And okay. Yeah, I should have written it the other way around, but anyway. Okay, maybe let me write the numerator the other way around. So probability that it's actually k, right? Because we care about one particular fixed k times the likelihood. Okay, and now this looks a little bit familiar. So now this is exactly the Q. So QKN. That's exactly how we defined that to be. So here is the Q. It's normal distribution of X given that you are assigned to cluster K. And it's divided over the sum of all these clusters. So that's what it is. Let me write it in full details, trying. So what's the probability that Zn happens to be K? That was our definition, right? We defined the generative model. We've designed it such that this is pi k. And then the second question is, what's P of x? Yeah, it's normal distributed from cluster K. Now that we know which cluster we belong to, that's very easy. So normal distribution given the parameter mu and the covariance sigma. Okay, that's the numerator, denominator. Same thing, but not with k, but with any potential cluster j. So. Okay, that's all. So now you can see here are the parameters coming in. And okay, if I want to be fully precise, I should say that everything here was conditioned on the parameters. So that's what it is, and now we are done, because this is really the definition of the QKNs, right? They were designed to be that. So we chose them to be this value, not because of what I just showed you. We chose them for a different reason. We chose them such that our optimization models happen to coincide at where we currently are. That's one reason you can choose them this way. So now we have an interpretation of why it's a good idea to choose them to what they are from this generative model perspective. Because if you choose them what they are, then they happen to be exactly this probability to which cluster you belong, right? So are you 90% red and 10% blue? That's exactly what's happening here, right? For one data point, is it more red or more blue? So that's what these probabilities describe. And that's why the Qs have a meaning, and that meaning is that they are a soft assignment. So you can come from both ways. If you like this interpretation more, you can start from here, so that this is a good idea to do. Or you can start from the other side, like we did in the beginning, and say just I want to optimize a function, and I'm doing it in this strange iterative fashion. But now we know the interpretation of these Q variables. Is there any comments on this?
Which are the assumptions?
The assumptions? Yeah.
Do you make any assumption to derive this interpretation?
What assumptions did we make to get this equality? That's a good question. And no, actually no assumptions. I mean, this thing, base rule holds anyway, no matter what you want to do. So that's not any assumption made. There is a bit of an assumption here, right? So here we say, yeah, that our data comes from the Gaussian K. So that's the assumption. That's the generative model that we have used. We have chosen this model of nature. We have chosen that every data point comes from a normal. So that's where assumptions are made. Otherwise, no assumptions, yeah. But very good question. Let's actually see. So this could lead us to the next question, that can we use this principle more generally if you have other probabilistic models, right? This is not the only choice you could make, saying that data comes from K Gaussians, right? You could make other nice generative models. And that's exactly what is the very last thing I'd like to discuss for EM, and that's here. So here you could talk about a very general generative distribution. So, and again, well, maybe that's given by the joint. So you have some hidden variables which you don't know, but they might have different meanings that we have just seen. You could be creative, defining different generative models. The question is this algorithm, the EM algorithm, is it still useful? So could we still optimize something like the marginal likelihood, which, remember, was the probability of X no matter what the Z's are? So that thing, right? Can we use the same technique to do this in general? So that's, and we'd like to maximize this. Find the best parameters such that this achieves the maximum. So, and the answer is yes, you can exactly do the EM algorithm, and it's going to be basically this. This will be your Q and K quantities, and in every step, you're not going to optimize the full model, but you're going to optimize a simplification again, which was like this simpler lower bound that we did. And here is the generalization of that lower bound. That's this quantity here. And I'll explain a bit in more detail after the break. And then we're done with EM algorithm and move on to matrix factorizations. Okay.